In this video, 13.3, we're looking at the birth of stars in the sun, how they start out, and how we achieve nuclear fusion. First thing is stars have a life cycle. They have a start, they're going to have the middle, and they're going to have an end. Most of their time, of course, is spent in the middle. Let you copy a few terms here. A nebula is basically a disorganized collection of materials. Things that include dust and hydrogen, helium, and other gases that have been ionized. For whatever reason, these particles decide to get together. And as they come together and get closer and closer, you concentrate the mass. And as the mass concentrates, then you increase a gravitational field. And so then you get more and more material being drawn in. Well, as the material rushes in, you will generate some heat. And you may generate enough heat to fuel something called nuclear fusion. And if you have hydrogen present, hydrogen is capable of nuclear fusion. And that's something we'll look at now, but also in chemistry. Now, two hydrogen atoms, why is it called nuclear fusion? The nuclear means nucleus. And in the nucleus of an atom, we have protons. And it's very hard to put protons together because they're positively charged, and we know like charges repel. So it takes enormous heat and pressure to force these different hydrogen nuclei together to get nuclear fusion. But if we have enough heat and pressure and we get nuclear fusion going, all of a sudden we can start generating heat and light, and our star will now be born. So now we look at nuclear fusion. We have a chemical equation for, well, actually that's a lie. We have a nuclear equation for it. And this is showing the nuclear symbol for different forms of hydrogen atoms. And when they get together, they end up making helium. And so these are two elements that we know we're going to find in stars. You're going to find hydrogen as a fuel and helium as a product of nuclear fusion. You're not going to be responsible for this reaction this time. More when we get to chemistry. Well, in order for nuclear fusion to happen, it should mention that it requires extremely high temperature and pressure. Now we move to the midlife. So stars are chugging away through their fuel, the hydrogen, and as they do this, they produce heat and light. The size of a star is a balancing act. The heat is wanting to force it outwards, and gravity is pulling it inwards. And so those two forces are balancing out and will dictate the size of the star. Our sun happens to be roughly halfway through its life. It's believed to have been around for about 5 billion years, and it's believed to run out of fuel in about another 5 billion years. Now we want to look at the structure of a star, in this case the sun. And so we'll let you copy down those terms. We're not going to have you memorize all these temperatures and things, but the core obviously is the center of the sun and a staggering 15 million degrees Celsius. Then we have a radiative zone, a convective zone, so convection's occurring there, a circulation of heat and materials. We have a photosphere. Photo means light. That's why it says it's a visible layer. We have a chromosphere. And then the outside, we have the corona, where the temperature is actually higher. And then you have a picture here, and I believe you have a picture in the 13.3 booklet. You may know that there are dark spots on the sun that are called sunspots, although hopefully you're not looking straight at the sun to find them. And that solar flares will emerge in times of active sunspots. And there are things called solar prominences and the solar wind. And we encountered solar wind briefly when we talked about magnetism. And that's where the solar wind, which contains ionized particles that go outward from the sun, get aligned by Earth's magnetic field, and we can get the northern southern lights. Well, that's really it for that section. And so there will be a number of things to work on, and you'll get about a week to take care of those.